Our project deals with implantable medical microconnector. Our advisor is Dr. Jones. My name is Maria Marta Lopez. This is Eric Doan, Samuel, and James. So an issue we wanted to address is basically that there's diseases that affect people worldwide, such as neuromuscular diseases, as well as ailments involving hearing loss, migraine, stroke, chronic pain and prosthetic limbs. Oftentimes these are treated through painkillers, surgery and injections, and this can affect a person in their day-to-day life. So in order to have a less obtrusive daily event, people have opted to use a neurostimulator device. Neurostimulator devices are used for more severe cases, but this is an improved alternative in comparison to painkillers and surgery. There are varied issues related to the neurostimulator device. The biggest one is that it is currently hardwired, so this makes the interchangeability of the device very difficult for the doctor. If he has to replace, let's say, the leads or the neurostimulator, he would have to remove the entire thing from the body rather than just removing a part of it. Moreover, it's too large for the human body for such a low channel count. Currently, there's only 16 channels available in commercial use, and this can't account for diseases that require higher stimulation. Moreover, it's an electrical component that's going to be placed inside the human body, so we have to make sure that it is hermetic. And now Eric is going to discuss the objectives of our project.
All right, so we had several things that we wanted to accomplish. Number one, we wanted to create pins in HDCC and LTCC. We wanted to make a microconnector with 32 pins. We wanted to minimize the size and have no sharp edges. Also, we want to make it with biocompatible materials, make it user-friendly for the physician, so when he's actually in an operating facility, that he can easily handle the connector and be able to make the connection. We want to test for conductivity and hermeticity, and then we want to add sensors for use in artificial limbs. Now, the design requirements is number one, 32 pin connections, pins on one side, and then vias on the female side. An O-ring design for the hermetic seal, create a way to keep the design clamped together. Also, we wanted to do a pin orientation so it made it easier for the device to be able to connect it, to be connected. And then we needed to have conductivity between the pins and the vias so that we have the electrical connection going through. And then attach the leads to the pads, and then also we wanted to add strain relief. And now for our initial designs, Sam will present that.
So this was our initial design idea, the first alternative design that we had. We developed the 4x8 pin array, and with pads and with the pads being connected to the top side of the microconnector. This was a good design for pin orientation, but it lacks the O-ring design for hermetic seal, and also it doesn't provide any type of strain relief system for the wires. For the next design, we had a 6x6 pin array, which would allow for 36 pins or connectors. O-ring design was incorporated in the connector itself in the LTCC or HTCC, and the pads would be located on the top side or on the back side of the microconnector. The problem with this design is not streamlined, so it takes up more room in the body. So then we opted for an additional design, which is the design alternative 3. And this was our proposed design, where we'd have a 3x10 pin array plus one on each end, giving it a more streamlined design, in addition to an O-ring to the design to provide the hermetic seal, as well as the pads would be located on the top side of the microconnector itself. And now James will talk about manufacturing process.
So a big aspect of this project is determining the manufacturability of the actual parts that we want to make. We start off with LTCC or HTCC sheets, which are pliable and bendable. These sheets are then precision punched in the lab with the design. After punching, the vias are filled with either silver or graphite, depending on the layer application. And then, these are filled using a bladder filler, and after which they are then sheared using a shearing device, which ensures that we get proper filling of all the vias, because we want to ensure that we get good connectivity throughout all the layers. These sheets are then placed in the oven to solidify the inks that we use, after which there'll be, the layers will be stacked and laminated. And then these laminated stacks will then be co-fired and later assembled. These are some of our initial manufactured parts. In the beginning of our design, we wanted to make sure that we can make these pins because they're something that have never been made before. This is our prototype that shows the pins that we were able to make on the right side, and on the left side you can see the relative size when compared to a dime. Next, I'm going to talk about some design difficulties. Sorry. Some design difficulties that we encountered are the manufacturing process, the screen printing. As you saw in the design alternative 3, we saw some screen printing which led from the pins or vias to the pads, which the leads will then be attached to. This is an issue in the manufacturing process because screen printing involves a lot more work in the design phase as well as in the actual manufacturing lab. Also, cutting out a groove for the O-ring to be hermetic proved to be an issue because it was so small. The alignment of the pins, again, because it was so small, and the nature of the pins and the ductility led to some problems, as well as adding a strain relief to the design. And now Sam is going to talk about some design alternatives.
So some design adaptations or alternatives we came up to the ceramic part itself is to add the pads directly to the back of the ceramic part, which would, like James said, eliminate the screen printing process. In addition was to create a housing for the ceramic part itself that the microconnector will be placed in, and that housing will be molded around the ceramic part. Also, the O-ring will be placed in the housing itself to provide the hermetic seal. And in the housing itself, you would also have alignment pins that would be able to orientate the pins of the microconnector because they are so small. And also a strain relief added to the housing itself to provide So here we show the screen printing process that we eliminated. As you can see from the first image, we have the design with the screen printing inlaid inside the LTCC, inside the different LTCC layers. And on the bottom, we just show the complete pads on the reverse side, which simplifies the design a lot and makes our life a lot easier when we're dealing with manufacturing. Or if it was to go into production, it'd be a lot simpler to manufacture. And what we can see over here is alignment pins added to the design that would align the two halves together and all the pins together because those pins are relatively small in diameter, about 250 microns. And also we have the O-ring groove inserted in the housing itself, as well as you can see the strain relief system added to the design. So over here we see the comparison from the proposed design to the final design that we came up with. This was the initial idea where we would have the pins connected to the ceramic part itself, as well as the O-ring groove in the ceramic part. And what we have here is the final design with the ceramic part, with the housing being molded around the ceramic part and the O-ring in the housing itself. And what we have here is the fully assembled microconnector rendering. We have an isometric view. The two long shafts coming out is a representation of the wire itself. And on the bottom, we have a top view of the microconnector itself. And Maria Martha is going to talk about rapid prototyping.
So in order to explore the different options we had to manufacture our housing, we decided to see what rapid prototyping had to offer. We first contacted a company called Fine Line Prototyping, and they gave us a quote for only one half of our housing, and it was about $200 for just half of it, and obviously that is far out of our reach monetary-wise. And so we started finding other companies. There's a company that uses a Stratasys 3D printer, and it has a very high resolution, and it can print in micro sizes due to its micro dispenser. And we contacted a company called WB Engineering, but they have yet to give us a quote. So both Stratasys and Fine Line Prototyping, they use materials that aren't biocompatible to be inside the human body. They use materials that could be on, like a hearing aid, it could be inside, but like inside your ear, or for prolonged use on your skin, but not actually inside your body. but there's a technique called two-photon polymerization, which basically uses ultra-short laser pulses. And these pulses emit 2 photons, and then they later polymerize, and they create a 3D material. So this technique, 2PP, is better in comparison to the rapid prototyping provided by the other 3D printers because it has a higher structural integrity as well as a higher resolution. So the University of North Carolina has improved the 2PP process because they discovered that by using riboflavin, which is available in all of our bodies as vitamin B, and in combination with triphenyllamine, and using this combination, it makes the photoinitiators into PP. Instead of it being synthetic, it's now biocompatible. And this process has now been implemented in tissue engineering as well as wound dressings and even implantable devices. And they've been printing very micro-scale devices, which obviously is beneficial for ours. However, because it's not readily accessible to us, we finally decided to just go with the MakerBot replicator available in Dr. Basil's lab. They use a material of polylactic acid, also known as PLA, and it's very cost-effective and durable, and it could basically prove what we needed to prove, that it could be printed. So these are the parts that we manufactured using the MakerBot. This is the initial design with the strain relief attached to the housing. We have a scaled up model to compare it to the actual size, and you can see obviously that the scaled up model has a better resolution than the actual size, which is only 15 millimeters long, including the strain relief. For our updated parts that now no longer have the strain relief attached to the housing, you can see this compared to the dime. And as I mentioned earlier, we now had to separate the strain relief from the housing. This is because the housing has to be a different material than the strain relief because it should be rigid in order to protect our ceramic part. And the strain relief, we wanted it to be made of a more flexible material in order to provide stress relief on the lead, since it has a vulnerable point when it comes out of the housing. And also by separating the strain relief, we could implement the Veteran Affairs design, and this basically saves money for them since they could use this part as well for their device. And now James will be discussing the electrical connections.
Right, so until we considered these options, the electrical connection was left up to simply inserting the pins into the via slots and relying on that just physical mechanical connection to ensure an electrical connection. To us, this was not a reliable connection method, so we wanted to consider some different options. One option was to manufacture a spring that would fit inside the vias, a conductive elastomer, which would provide some flexibility, but also with the nanoparticles of platinum implemented into it, it would ensure a good electrical connection, and as well as creating a nanometal spring, which would be similar to the first option. Some options that we did attempt, because we could not get the spring manufactured, and because of the readily available fuzz button that we see here in this picture, we used the fuzz button, which is really just windings of beryllium copper wire, which are gold plated, so they are biocompatible, and these are readily available. We have them. They're provided to us by the VA, and these are pliable. They are flexible, and they ensure good electrical connection. The conductive elastomer was also attempted in our prototypes, which is good. It gives good electrical connection, but it's not as reliable as a fuzz button. So we did want to use a fuzz button for our prototype. And using this fuzz button, we had to increase the via size to 380 microns on an 800 micron pitch, and this change in the pitch led to a change in the pins as well, and we increased the pin size to 250 microns. We also wanted to add strain relief of a separate material, as we stated before, adding clips to hold the halves together, the two housings, and the final design, the size of the microconnector is about 1/2 inch long, 1/4 inch wide, and 1/4 inch tall. With the added strain relief, the final size is increased to about 1 inch. now Sam's going to talk a lot more about the final design.
So the final design consists of a housing, the ceramic parts, O-ring, strand relief, and the clips holding the two halves together. The housing material will be, if it were to be molded, it'd be made out of PEEK. It has good biocompatibility as well as good physical properties. The strand relief material would be medical 4850 silicone, and the O-ring would also be medical silicone as well. What we can see on my right side is the female ceramic part, and on the left side will be the male ceramic part. Over here we have the assembly of the male and the female parts in the housing. So this is how it would look. From the previous design, you can see we added slots to the for alignment instead of pins. It's more reliable, and even if you were to get it manufactured, it'd be cheaper to manufacture. In addition, we have the O-ring as well as the ceramic parts encased, and we have grooves for the two clips that would be holding the halves together. And over here we have a fully assembled microconnector. This is what it would look like when it's fully assembled. We have the front view, top view, an isometric view, and an exploded view of how everything would come together. So these are just some of the major dimensions in our design that, like James explained, we have about an inch long, including the strand relief, about half an inch, or just a little over a half an inch. The housing, the height is just about a quarter of an inch, and the width is just a little over a quarter of an inch. And what we have here is the updated ceramic parts with increased via size that was obtained in the lab, that we manufactured in the lab. The pins were increased, like James said, to 250 microns. The vias, or the holes, were increased to 380 microns. And what we can see here in this one is the fuzz button in the actual hole itself. And future design considerations to the ceramic parts would be to add layers on the bottom side where the wires would come in to connect. This would add a more compact design, and it would allow for the wires to easily stay on top of each other and layered. And now we have Eric talk about testing.
All right, we have several tests that would need to be done. Number one is, first and foremost, is conductivity. We have to ensure that the electrical current coming in is coming out from the male to the female side. And then we want to use the MIL standard 883 test standards. This is military standards for microelectronic. This includes various tests for electrical, mechanical, and environmental tests. One of the specific test conditions is test condition 1014. This is the seal test to test for hermeticity. Now, our objective evaluation, our number one goal was to create pins in the LTCC and HTCC. This was accomplished in the LTCC. Initially, we ran into several problems as we combined HTCC and LTCC. We could not get the HTC to come apart. The pins would fall apart, and it was unsuccessful. Through several attempts, we made a modification. We punched a silver tape and combined that with the LTCC. When we put that in the furnace, the carbon burned off, and which ended up resulting in leaving us with pins. Now, with this design here in the middle, this was actually 3 layers of silver combined together. We realized that the pins were not very clean, and we wanted to address that situation. So in our final design, we only made it 1 layer for the pin to make it cleaner and have a better connection, because we also had high ductility. As you can see, this is kind of folded over. We wanted to prevent that as well. So we made the pins wider and then also shorter. Also, we wanted to make a microconnector with 32 pins. This was seen here, an 8x4 grid array. We wanted to minimize the size and no sharp edges, so that obviously this would cause no damage to the interior of the body. We want to make it with biocompatible materials. Thus far, this has not been accomplished, as we have not completed it in the HTCC. The HTC is already a confirmed biocompatible material. We have not achieved that yet. We want to make it user-friendly for the position. We did that by adding the housing and then the alignment pins. And then test for conductivity and hermeticity. We have tested for the conductivity and found out we do have a good connection. The hermeticity, we have not accomplished that yet, as we have not got the housing and O-ring assembled. And then our ultimate goal, if we could have got to it, was to add sensors for use in artificial limbs so they could sense force and whatnot. We have not been able to get to that part of the project. Now, for the cost analysis, Our prototype cost us $56, and with the graphite being the bulk of our cost at almost $35 of it was graphite. And then the projected cost for the microconnector is $531, as each fuzz button is $5, so that comes to $160 for the 32 pins. And then the platinum paste, that accounted for most of our costs. And then Maria Martha will take it from here.
So this is the timeline for our project, which started obviously last semester until now. And for our global component, we wanted a basic awareness for a need for a connector like this, since there's various ailments that affect people worldwide. We also wanted to set the foundation for a device such as this in order for more research to be done. And upon making it biocompatible, hopefully it could be submitted to the FDA using the military standard testing, as well as the EMA, the European Medicine Agent, using their testing standards, which are ISO 10993. And we also wanted to make a device that was as cost-effective and sustainable as possible. So finally, overall, we can conclude that we did make a microconnector with 32 connections, which doubled the amount of connections in comparison to a connector that is only 16. We were able to fix the issues with alignment by putting pins on the actual housing and making it easier for the doctor to align the device. We also were able to improve the manufacturing process by eliminating screen printing. And we added the strain relief for the leads. So we could conclude that a biocompatible microconnector is possible as long as the funds are there, but there is further research and testing that is needed. Overall, we want to give a very special thanks to Dr. Jones, who's the brain of our project, as well as Dr. Carvazzi, and for the people present here, Dr. Basil for allowing us to use the 3D printer, and Omar for helping us with the 3D printer. Questions?
All right, very good. Well, we're over 2 minutes, so bear that in mind and making some adjustments. And I hope you recognize the dress code for next week.
Yes.
Of course.
Okay, so Dr. Basil, you lead off, and I have a few questions.
Just in the beginning, so I think you guys did a really nice job, and I like the fact that you laid out your goals and then you discussed at the end what goals you made and didn't. So that's really important. Sometimes we lose that. I would say couple forward, just in terms of presentation. Back to 1, 2, 3. 4, 5, 6. Sorry, keep going backwards. Never mind. So the first time that you talk about LTCC and HTCC, you talk about them in acronym form. And so a lot of times you're going through the presentation saying LTCC, HTCC, and back and forth. And without a good introduction of those two things, it becomes very, very hard to follow exactly what you guys are doing. So maybe just take one slide, and I know you were over a couple minutes, but take one slide and just discuss the materials a little bit.
Yeah.
I would say, okay, let me see what else I have here. So a couple of the engineering drawings are just a little bit hard to see, so in terms of presentation. Especially there was one specific output from SolidWorks. It probably looks good on your computer, but just the fonts with it's near the end. It's
That one too, that one.
With the dimensions.
Yeah, with the dimensions. Yeah. And you guys are going to bring the little.
Yeah.
Yeah. So that helps a lot.
And a
You can
microscope.
see them. Yeah. Right. Yeah. Right. And so you did run a conductivity test.
Yes.
Okay. So it might be worth discussing what you did during that test and what conductivity did you measure, right? So, and what is the limit that you're interested in achieving? I mean, conductivity is a full range, right? So, just state, okay, this is what we measured, this is the output, this is what we're looking for, all of that, right? The one other question I have is about the fuzz buttons. So, the fuzz buttons themselves are biocompatible?
With the gold plating, yeah.
With the gold plate. Okay, just because if you disconnect it in the body and you have those, so
Right.
if I'm assuming this correctly, right, you put them in between to reinforce that connection for maximum conductivity?
Yes.
So if you're disconnecting this in the body, would those just be free? Okay,
No.
so how does it work?
Well,
Yeah.
the way that we did it, we also, we took a silver kind of paste,
Okay.
put it in the vias, which have some adhesive binders in them, which hold the photon signal. So you can like pick it up, turn it upside down, and fall out.
Okay, but all of, so I guess what I'm saying is the connector can be in the body, right?
Yeah.
And so all of that just has to be biocompatible. So as long as it is, that's okay. I just was curious. I didn't know for sure.
One of our main goals was to, in choosing all of our materials, to try to pick biocompatible materials in the case that there is a leak or something.
Sure, right.
Biocompatible
Yeah, just
materials.
curious. Yeah, right. I mean, if you can hold it upside down, it's one thing, but if you can connect and disconnect, that's the whole point, right? So just the robustness of that, I'd just be interested to know more, but you know, it's fine. Yeah, I mean, as long as through the process, that's something that is not. Yeah,
And one thing you should indicate, I think, is that the LTCC was chosen to show process development. We had the capability of doing this. No one's ever made pins out of powders before.
Right.
That we know of. But we've already developed all the co-fired alumina. It's just that every time we make an ink, it's $2,000, and you know.
Makes it tough for.
And so we didn't quite get there. But the whole objective is to make sure that the processes that we manufacture with are compatible. So we did the same thing when we did the high density feature. Made it first out of LTCC to make sure that we weren't spending lots of money making these, and then we moved over to the high temperature co-fire. And the other components we feel will be able to be molded, and some of the things we couldn't test because we didn't have it is we wanted to try and weld. The leads typically are 1 mil platinum wire.
Oh, yeah.
The impedance isn't really great in these things. Typically you can stand with 1K ohm and not have any effect on neurostimulators. But the things that I think they need to sort of emphasize is currently these are commercially done and there are 16 channels. But when she says hardwired, they're welded. And so if the pulse generator dies, you have to remove the whole thing. And the problem with neurostimulation is you want the nerves to go around the electrode. And so it's like in a pacer, they never remove an electrode. If the pacer electrode fails, they just cut it and stick a new one in there.
Really?
But that typically only has one lead.
Yeah.
And so here, and so that's the whole thing, is whether we could do something that would be part of a kit, so the doctor can insert the electrode and then the stimulator could be replaceable. Because often they use external RF coupling to recharge capacitors and things like that. So the patient's always dependent on the device, thinking about the device, and you want to try and break that dependence.
Yeah, it makes a lot of sense.
So do you think next week we should touch more on that?
Yeah, I mean, it's a little bit tough, you know. Yeah, and the introduction, I think, to the project takes quite a bit, just for everyone to understand exactly what they're working on, you know.
But we should touch that this is a proof of concept, right?
Yeah.
And that's what I would say. It's a proof of concept.
Yeah.
But that the processes that move from this proof to the next step have already been developed.
Right. It's the same
You know,
process.
And you can reference the high density feed through, which is in alumina, and you can say that was the progression that was made.
Right. Okay.
So you already know if you can do it in LTCC. Then you can
And the other thing you should emphasize is that this is a project that is currently using pogo pins and other things that's probably 3 times larger in size, being funded by the VA. And so we took the task of seeing how we could miniaturize this.
As a segue to all of that, to what extent have you done some consultation with somebody? Well, first, let me back up and ask, are you multidisciplinary group?
Mechanical.
We're all
Yes, all mechanical. So that begs the question, to what extent have you consulted with the physician or the biomedical folks to make sure that this process will be accepted by the human body?
What we've done is we spoke to Sonny Behan. He is a designer he's an outside consultant who all his design work is primarily in biocompatible materials, implantable devices. So we
So
consulted.
somewhere say that you've done that consultation to get some real valuable input to the acceptance of the human body.
And then also Dr. Kinsey Jones, because he's worked with implantable retina, and so the materials he's familiar with, whether they're biocompatible.
Okay, all right. And use the laser a little bit more point out some of the things, because there's a lot of little details there
Yeah.
that you addressed, and it gives a little bit more focus to the audience if you use a laser. I think we got about 2 or 3 of them out there. Let me see here. Oh, yeah, theoretical analysis. There's a lot of details there on testing and validation and all of that. I don't recall seeing any theoretical analysis that preceded that. Is there any?
There's actually none on the slide. There is some in our final report.
Bring in some of that, because the IFD folks are going to ask you, where did you do some analysis? At least some original analysis or some comparative analysis or something like that to bring in the theory. So I think it would be a good idea to bring in some of that, recognizing you're over time already, so you probably have to do some finagling to make that happen.
Yeah.
Okay. Let's see, there's a slide on design adaptation. I have a note here. Can you bring that slide up? I'm not quite sure why I need that. Design adaptation. Oh, yeah, back up. I think it's up. Let me see, go back again. I'm going to go forward. Forward again. That one there. I think it's,
Yeah, the font.
that's not very clear. I think that's what that's what my note was suggesting, that you may want to do some work on making that a little clearer.
Yeah.
All right? And go to your final design slide. Okay, let's see all of them. Go back. That one.
Yes.
I think that one there, I think, so it's a busy slide, so you may want to take a good look at what you really want to present and focus on that. And
Yeah, you could probably crop out all
Yeah,
the
that's
what I'm
saying.
others. Yeah,
Yeah, we can just put,
yeah.
And even just one view.
Yeah, right, you don't, yeah,
yeah,
just as a reference, you just need a couple dimensions,
Right.
yeah.
exactly. And, well, what are the units of those dimensions?
Interest.
Oh,
If you're able to read the bottom part.
yeah, well, which we can't, so that's the point, okay. All right, those are my comments. In closing, I would say also, make sure you review the rubric upon which you will be evaluated, so you know what the expectations are of the IAD folks sitting here. And there's some line items there, and they're gonna be plugging in numbers based on what you present. And if you want to get a good score, you need to be cognizant of all of that, how you're going to be scored. So that's in Blackboard in many places. I think I also
Yeah.
said. Okay, so take a good look at that and make sure you address that.
there are some things that are on the rubric, but I don't think
Whoops.
I'm alive, I made it.
I don't think that they really apply to our design. Like, there's things like economics, like environmental factor. It's such a small design that I don't know how we would address it.
Okay, let me see what you're talking about.